Hello, I'm Trevor Hodgson. I work for Atkins, who are a member of the SNC Lavalin group. I'm currently speaking to you from Aberdeen in Scotland, and where it's dark outside. We are very pleased to be able to present here at the first UK Offshore Wind Day. The webinar that I'll be presenting with my colleague will be on the concept selection of wind turbine substructures. I hope this ties in nicely with the other presentations which you have received as part of this series of webinars. As mentioned, I'm Trevor Hodgson. I've been working for Atkins since 1977. Most of that time I've been working in the offshore oil and gas industry, doing a mixture of steel structures, aluminium surface craft, concrete gravity-based structures, also working in software development and the nuclear industry. Since around about 2000, I've been involved with the offshore renewable industry, working in the wind, wave and tidal sectors, but most recently been involved with the design of monopile, jacket and concrete gravity structures for the offshore renewable sector. And this is what this particular webinar is going to concentrate on.
Hello, my name is Matt Lehrer. I've worked for Atkins since graduating in 2013. I joined the Edinburgh office in the UK, originally working for the oil and gas offshore structures team. I transitioned a few years ago into the offshore wind team, and I've mainly worked with offshore jacket substructures. Unfortunately, I don't have a working webcam at the moment, so please forgive me for the missing video.
Well, thanks, Matt. Matt will be helping me through this presentation. SNC Lavalin were founded in 1911, and they are a truly global company, specialising in the built environment and making our world what it is today. We have teams that work throughout the lifespan of projects, all the way from helping with capital investment through the consulting, the design, the engineering, the construction, making sure that the capital through the project is sustained, all the way through to operation, maintenance, and eventually decommissioning. We have clients in many industries throughout the world, in oil and gas, in nuclear, in mining, metallurgy, infrastructure and power, to name but a few. In 2017, SNC Lavalin acquired Atkins, who were already one of the world's largest and most respected design, engineering and project management consultancies. The fit of Atkins and SNC Lavalin was ideal, each complementing each other's skills and operating in different territorial parts of the world. Now here is just a little of what we do as SNC Lavalin. You can see around the ring in the centre here all the different industries that we work for: oil and gas, decarbonisation, digitisation, electrification, industrial and manufacturing, cities and communities, and transport, both catering for the demand for services and the supply of those services. Around the outside here we have some of the major projects that we've worked on. Now, I mentioned that SNC Lavalin were a truly global company. We in fact work in 50 different countries throughout the world. We have 50,000 employees at the last count. Those employees are from 130 different countries in the world, and we speak 70 different languages. Certainly not me personally, I only, I'm afraid, contribute one of those languages. So we move now to Atkins, and in particular their involvement in offshore wind. As you can see from this slide, we cater for most aspects of the design and indeed the operation of offshore wind farms. About the only thing that we don't actually do is the design and building of the offshore wind turbines, but we are involved in almost all other aspects. We undertake studies that at various levels, the overall design of the wind farm down to individual components. We handle permitting and consent for the wind farms. This is the main area that we're going to talk about today, the concept design of offshore wind farm support structures. We also do front-end engineering design and detailed design. We don't operate installation vessels ourselves, but we do manage those. And we look after the structures throughout their life, asset management, operations and inspection, structural integrity management of those structures. And we provide a number of different services for the offshore wind sector as well. Now, this is a slide with a few key numbers on it. We have 45 years of experience in the oil and gas industry and 18 years in offshore wind. We've now fully designed about 20 offshore substations. We've again fully designed 375 wind turbine support structures. We have some 300 staff who work in different sectors of the industry: electrical, geotechnical, safety, and structural engineers. We've been involved in the various stages of 11 different floating wind projects, all the way through to detailed design of those. And we look after, very important aspect, we take the structural integrity management of some 1,000 different offshore wind structures. Mentioned down at the bottom here of the virtual wind farm tool, I will talk about that later in the presentation. Now, here are a few key examples of projects that we've worked on at Atkins. The Beatrice wind farm, jacket structures for offshore Scotland, Dudgeon, 67 extra large monopile foundations, Triton Null, even larger turbines for those monopile structures. We acted as owner's engineer for the Blythe demonstrators for EDF. Those are concrete gravity platforms. We have designed the wind float demonstrator and other offshore floating wind farm structures, and we have a major track record in the design of offshore substations for various wind farms. These are a few other major projects that we've been involved in. We're still just finishing off the Cumbria wind farm, jacket substructures for the 62 different locations across that farm. Offshore substations, the Baltic Eagle, we're just completing. We have been involved with the feasibility design of the Kincardine offshore floating wind farm. We look at integrity management, asset integrity management of different structures, lots of different wind farms, covering some 1,000 structures, as we mentioned earlier. We have a very strong geotechnical team help and assist us with the design of the foundations. And we're doing electrical work as well on the export cables, in particular for Hornsey 4. The last slides describe a little bit about who we are and what we do. Now we get on to the concept design of substructures. First of all, pass you across to Matt to talk a little bit about common fixed structure types that we may select from and what the design advantages are for each of those. and then I'll come back on and talk a little bit about the selection criteria that we might employ to decide what types of structures to use.
The key drivers in support structure selection are water depth, soil conditions, and turbine sizes. There are a number of other parameters that are important in substructure design selection, such as the mid-ocean conditions, like the wave and wind conditions, the seismic conditions, local fabrication facilities, available installation capacities, and environmental requirements. There are a range of typical fixed-bottom WTG substructures available for designers to utilize, such as monopiles, jackets, concrete gravity-based structures, suction piles with monopiles, and suction piles with jackets. Monopile designs have been utilized across the world. There are a number of benefits to these designs, such as they are very simple, they are easier to fabricate, they're very efficient in shallow waters, and they require little to no seabed preparation. Jackets are designed with either 3 or 4 legs with a range of different brace configurations. Again, they're a mature solution that requires little to no seabed preparation, with jackets suitable for deeper water depths. Concrete gravity-based structures can be self-installing, as they don't require any piles, there are no pile driving noises, and can realistically have an extremely long design life, so can be repowered. Suction piles can be installed in a single operation and can be removed at the end of its service life. Installation is almost silent, and it generally requires little seabed preparation. Suction buckets can also be used with jacket designs, thereby reducing the load through each bucket.
Well, thank you very much, Matt. One key thing we're trying to bring out here is how rapidly the design of offshore wind turbine structures has been changing in recent years. Just 10 years ago, we were looking at turbine sizes up to 5 megawatts, rotor diameters less than 100 meters. Gravity-based foundations were being used in shallow water only, and monopile structures were restricted by the behavior of the soil and what you could actually build, what diameters. Jackets, tripods, and tripiles were accepted in deeper water, but the industry anticipated that floating structures such as the spar structures at high wind would be used for deeper water. The maximum water depth for monopiles was considered to be around about 30 meters. However, it was realized that monopile structures in particular were behaving better than was anticipated. So this instigated the PISA project to look into the performance of soils for very large diameter monopiles, and that did indeed show that the soil performance was much better than originally anticipated for smaller diameter piles. Coupled with other technology improvements like the ability to roll larger diameter and thicker steel pipe, improvements in installation vessels, pile driving technology, noise mitigation, and the fatigue performance of welded joints allowed monopile structures in particular to grow significantly in size. As a result of this, the suitability of foundation types was able to be extended to consider larger turbine sizes and over deeper water before you have to switch to floating structures. So the approximate extents that are shown here show where those structures might be suitable, but where these diagrams overlap, then the most efficient solution would be chosen, also dependent on soil properties at the site. As mentioned, soil conditions are a very important driver in the selection of substructures for wind turbines. In sand conditions, the suction piles tend not to be favoured because of the possibility of piping during the installation of the piles. Gravity-based structures tend not to be suitable on soft clay and would need dredging out of soft surface materials. And shallow rock tends only to be suitable for pile jackets, which can be drilled and grouted into that, or gravity-based structures which sit on top. And chalk soils are not good for piled solutions for jackets because of the reduced skin friction in weathered chalk. Some other design drivers are worth mentioning for substructure selection. In seismic regions where there is a risk of soil liquefaction, then certain types of foundation may not be suitable. Where there are typhoon conditions, these give extreme loads on structure, which may well be limiting in design and restrict the type of substructure that may be selected. Where there is a local limitations on the noise of driving piles, then it may be more suitable to use gravity or suction foundations. And similarly, where there is limitations on the installation vessels available, then deep water monopiles may not be suitable. Well, that introduced the types of substructure that might be selected for a particular wind farm. We'll now go on to talk about the design process which is used to progress the concept design. I'll start off by talking a bit about the objectives and the data requirements for that, and also a little bit about the wind farm layout. Matt will then take over and talk about some of the processes of selecting, clustering, and analysis requirements. And I'll finish off this presentation with an introduction to design optimization. The process through the design of an offshore wind farm can vary quite significantly, but this figure is a fairly typical approach. Concept design followed by front-end engineering design followed by detailed design. In the concept phase that we're interested in here, we're taking the data about the site, and we're using that to decide on a layout for the wind farm, a selection of the turbines, support structure selection, how those designs of substructures are clustered into groups, and what the initial sizing of those are. That initial layout can allow us to do more refined geotechnical surveys, to use data from the selected turbine manufacturer, and to use that information in a further design of the substructures. Some of the other presentations in this series of webinars will have described the data requirements for offshore wind farms. So I'll pass over this fairly briefly. Initially, though, we do need geotechnical data for the site for concept design. Subsequently, that would be refined for more detailed design. We're looking for climate and metocean data, the effect of the environment on the structure, and we're also looking for the effect of the structure on the environment, i.e. what local wildlife is there, who else uses the local ocean, and if there is any risk of unexploded ordnance in the vicinity. We feed all of that data into a tool that allows us to build a virtual model of a wind farm. Hence, it's called the Virtual Wind Farm tool. It takes all of that initial data, works out what the wind energy yield is, the amount of power that you generate from the wind farm, takes into account local databases of turbines and fabrication and installation facilities. And then it allows the selection of the turbine type, the substructure, and or the foundation concept by accumulating the through life costing of the development. That covers the design, the fabrication, the installation, the operation and maintenance, the decommissioning, and the financing of the wind farm. And finally, we can work out from that the capital expenditure, the operational expenditure, and the levelized cost of energy. And that allows us to select the most efficient design for that particular wind farm. This is an illustration of all the data that feeds into that optimization process. The turbine model, the cabling, the foundation model, the soil conditions, the OSP, the offshore service platform, the environment, the energy yield that you're getting, the capital expenditure from building and installing the sites, the operational expenditures, the locations of the individual turbines, and the financial model, how much it's going to cost to do that development.
Clustering is the grouping of designs to standardize construction and reduce design and analysis schedules. For example, if you have a site with 50 WTGs, you don't want to design a single structure to fit all 50 sites. You may want to design 4 or 5 different substructure groups or clusters. Clustering is dictated by the water depth variability across the entire site and the soil variability. For jackets, there's a structural limit to the maximum pile stick-up that you can use. For standardization and design, the upper part of the jacket and connection into the transition piece and the transition piece itself tend to be standardized across all the jackets. A common footprint across all clusters is strongly preferred, as then it only requires a single standard piling template, and it makes transportation easier due to requiring one configuration of C-fastening. For monopiles, clusters are defined by the pile diameter in the soil. Typically, they have a common TP across all sites and require a different conical transition length and slope to accommodate. Wall thicknesses and pile penetrations vary by location. Gravity-based designs tend to vary by location, i.e. clustering is not required. When designing WTG substructures, the dynamic effects of the turbine in C states must be accounted for. Turbine dynamic loads include the rotational frequencies such as 1P, which is a full rotation of all the blades, wind turbulence, the effects of each blade individually passing the tower, which is the 3P frequency, and the blade natural frequencies. The natural frequencies of the turbine, often known as 1P, 3P, 6P, and moving upwards, are often given as fixed values or a range of values in a Campbell diagram. Understanding these frequencies with the relevant margins allows for designers to target certain substructure frequencies. Other design conditions include strength, also known as ULS, fatigue, known as FLS, and accidental ship impact loads, known as ALS. Additional installation analysis may be required, such as transportation, lift, or on-bottom stability. There are a number of analysis approaches used by substructure designers, each with increasing analytical complexity. Broadly speaking, the analysis methods can be split into simplified static wind loads and time history wind loads. The simplified interface loads method is the crudest and is often used for preliminary concept design. This assumes that the turbine loads can be simplified and statically applied at the tower and TP interface. For example, a single point load, representing the maximum turbine load experienced, might be applied at the interface point. However, as the loads are simplified, there is no inclusion of dynamic effects and the method has limited accuracy. The superposition method allows for fatigue analysis to be performed using simplified loading. This assumes that the wind and wave fatigue analysis can be performed separately before combining with statistical approaches. The wind loading is simplified to a range of statically applied loads at the interface, representing turbine loads for different conditions across its life. The method can be used as a preliminary approximation of the fatigue lives. However, there are a large number of simplifications for this analysis type, such as aerodynamic damping is not well covered, the coupled dynamics are not covered, and it has limited accuracy. There are a range of coupled analysis methods available. The premise of these is to separate out the aeroelastic turbine model and loading from the substructure through the use of superelements. The superelements capture the substructure's stiffness, mass, and damping matrices, along with a selection of wave load time series. The superelements are fully linearized below the interface elevation, meaning that no nonlinear soils can be modeled. Guyon reduction is suitable for gravity-based structure design. However, it does not capture higher modes' dynamic response well, which aren't required for gravity-based structures. Therefore, it isn't suitable for jackets or monopile design. The Craig-Bampton superelement method is widely used by companies such as Siemens Gamesa. This method of reducing the superelement captures the higher modes more accurately and as such can be used for monopile and jacket design. The integrated approach captures the dynamic interactions of the substructure and the aeroelastic model in a single package. The wave and wind time series are captured simultaneously in the single software, without the need of superelements. This allows for nonlinear foundations to be captured. Packages such as DMV-GL's bladed software allow this to be done. However, the substructure model often requires simplification to run due to the package and computational limits. Wave load generation for time domain analysis is generated using C-state spectra and random seeds to assign initial phases. Seed variability is important for statistical reliability, i.e., we require a variance of C-states to ensure a range of structural responses is captured. As much as possible, loads are generated on the full structure, including any secondary steel like boat landings or J-tubes for the cabling. Extreme wave time histories for the strength ULS analysis include a single embedded deterministic wave, such as the 50-year extreme wave. For monopile and tripods, wave loading is typically very important, as it causes a dynamic response of the entire structure. Capturing diffraction effects is very important due to the resonance of the structure and the waves. Monopile design is often governed, ensuring that socketing or large lateral movements don't allow soil to be compacted at the pile head or tip, as this would reduce the contact pressure of the soil and piles at these locations. Grouted connection design is also extremely important for monopiles. For jacket design, wave loading is less important due to the structure being relatively transparent to the waves. Brace dynamics may be a significant issue due to the blade frequency interactions or vortex-induced vibrations. For gravity-based structures, shallow foundation design is critical, checking for overturning and liftoff. Concept design considerations for monopiles, jackets, and gravity-based structures can be seen here. For monopile designs, the key considerations are the WTG frequencies, the type of transition piece, the diameter to thickness ratio of the steel, the scour protection system, and the connection type to the TP. For jackets, the key considerations may be considered as the WTG frequencies, whether the jacket will have 3 or 4 legs, scour protection, pre versus post piled solutions, the framing configuration, the soil variability, and the seabed slope. For gravity-based structures, the key considerations are the wind turbine generator frequencies, the seabed slope, erosion potential, soil variability and the required preparation, soil stability and scour protection, diffraction wave loading, the fabricator capacity, and of course the installation technique. Typical jacket and monopile designs can be seen here along with the key parameters. The objective of each of these designs is to minimize mass and cost, but satisfy design requirements. For both types of structures, the interface height and pile embedment depth are critical. For the monopile design, key requirements might be the interface and mudline diameters, the cone dimensions, and the wall thicknesses. The jacket design is slightly more complex due to the number of braces and legs. Key considerations are the width of the jacket at the piles and at the TP connection, the pile stick-up, the bay elevations, which dictate the length of the bracing, and the sections of the legs and the braces. Although this list isn't exhaustive, it gives you some idea of the number of considerations required for the designs.
Well, thank you, Matt. I'd like to finish with just a brief mention of design optimization. Not only do we optimize across the entire wind farm using the virtual wind farm tool, but these days we can also optimize the individual designs of support structures at locations across the wind farm. And we do that by taking the design and analysis process that Matt has described and building that into an automated workflow. We also put into that the various constraints and the logic by which the design is achieved. And then we embed all of that into a design optimization loop, which will loop through the design using embedded logic to come up with the most efficient design for that particular structure. And here are some results of the optimization process. You can see in the figure on the right here that the mass and the diameter of an offshore monopile support structure have been reduced by successive optimization steps, while also always maintaining the design goals that we set for the simulation. So you can see the very significant reduction in mass and hence cost that was achieved for this particular structure. Well, that brings us to the end of this particular webinar. We hope you found it interesting. We are Matt Lehrer and Trevor Hodgson, and we work for Atkins, part of the SNC Lavalin group, and these are the principles by which we work. Thank you very much for looking at the slides and for listening. If you would like to find out any more, then our website is given on this slide. Thank you again.